Hi, my name is Wei Zhu. I'm a graduate student at the Department of Astronomy at the Ohio State University. In this short video, I will introduce the key results from my recent paper entitled Constraining the Oblateness of Kepler Planets. This work is done in collaboration with Chelsea Huang from Princeton University, George Zhou from Australian National University, and Doug Lin from UC Santa Cruz. Planets are not perfect spheres. In fact, planets in our solar system are more or less oblate in shape due to their rapid rotations. For example, for Jupiter, its equatorial radius is larger than its polar radius by 7%, and for Saturn, this difference is 10%. Quantitatively, the oblateness parameter f is defined as the relative difference between the equatorial radius and the polar radius, and the planet's spin obliquity theta is defined as the angle between the polar axis of the planet and the orbital angular momentum vector. The transit light curve caused by an oblate planet is different from that caused by a spherical planet with the same cross-sectional area. We refer this difference the signal induced by the planet's oblateness. Figure 1 shows some theoretical oblateness-induced signals for a Jupiter-sized planet in 100-day orbit around a Sun-like star. We derived an analytic estimate for the maximum amplitude of this signal in terms of the sky-projected oblateness and the planet-to-star radius ratio. This simple estimate tells us the maximum amplitude of the oblateness-induced signal is proportional to the projected oblateness and the transit depth. For a Jupiter-sized planet with a Saturn-like oblateness, the amplitude is no more than 160 parts per million. Such a small signal can only be detected with Kepler-level photometry. In this work, we present the first application of oblate planet transit models to Kepler sample. We first demonstrate the detectability of the oblateness-induced signal by performing a signal injection and recovery exercise. We injected 12 transits of a Jupiter-sized planet with a Saturn-like oblateness into the out-of-transit light curves of the KOI 368 system, and then applied an oblate planet transit model to the simulated data. The result from our MCMC fitting shows that the injected oblateness is recovered at a very high significance level compared to the case in which no signal was injected. We also confirmed that the oblateness can still be recovered very well with only a single transit. We then present the modeling of the four selected systems HAT P7b, KOI 686b, KOI 197b, and Kepler 39b. These targets were selected with the considerations either to compare with previous works or to pick up targets that are most likely to contain oblateness signals and easy to model. We provide the 1 sigma upper limit on the oblateness of planets HAT P7b, KOI 686b, and KOI 197b to be 0.067. 0.251 and 0.186 respectively. We also report a tentative detection for the oblateness of the 18 Jupiter mass brown dwarf Kepler 39b to be 0.22 plus minus 0.11. Because of the strong correlation with the projected oblateness, we cannot constrain the projected spin obliquity very well, but the posterior shows that the planet's spin should be highly inclined with respect to its orbital plane. Given the long orbital period of 21 days and an eccentricity of 0.1, such an oblateness, if real, is likely to be induced by rapid rotation. Assuming some simple interior structure of Kepler 39b, we estimate its rotation period to be 1.6 hours, much faster than 10 hours for Jupiter and Saturn, but still slower than the break-up rotation period of 0.9 hours for this object, meaning that such a fast rotator is not physically impossible. We also note that this object has a larger than expected radius. Its radius is larger by 20% than both theoretical predictions and radii of similar mass brown dwarfs. With the fact that a fast rotator is expected to inflate a little bit, we suggest that such a large radius of Kepler 39b could be explained by the oblateness measurement in our work. Thank you for watching this video. For more details, please read our paper which is posted on AstroPH.